Well, welcome back, and I do, as ever, hope you and your family are well. What we're going to look at today is thermal conductivity. It's not a very easy concept, so I'm going to do the video in two parts. The first part is the sort of Key Stage 3 GCSE part, and then the second part, if you want to watch that, is a little bit more tricky. So, what thermal conductivity is all about is how well a material conducts heat. So how well a material conducts heat. And it's quite a difficult concept, but you do know something about this, because I hope you've seen my video already on heat conduction through metals, and you noticed in that video that some metals conduct heat better than others. And what we're going to say is that a high thermal conductivity means that the material conducts better. So if it has a high number, and you can look it up in a data book, it means that the material you're dealing with will conduct heat better than a material with a lower thermal conductivity. So high thermal conductivity means a good heat conductor. Now, is this a good thing or a bad thing? So let's look at it in two ways. So firstly, if you imagine you're doing some cooking at home and you have a saucepan. Okay. A saucepan on a cooker, usually made of copper or aluminium, has got a thick metal base, and you want the heat to go through that. So with a saucepan, you want the thermal conductivity to be high. In other words, thermal conductivity is a good thing. Yeah? You want a high value so the heat goes into the material you're cooking. But if you're designing buildings, okay, particularly in the UK and places like that where we have changes of temperature during the year, then you don't want the building to lose all that expensive heat you're putting into it. So for something like a building, it's a bad thing to have a high thermal conductivity. So, you might have seen the video I've done on energy efficient buildings. And if you're going to put heat into a building, which is expensive, then you don't want to waste that heat. So you don't want to make the building out of things that have a high thermal conductivity. So as an architect and a designer, you're going to look for materials to build with that make sure that your building does not have walls and roofs, etc., made of materials that are a high thermal conductivity. You want the heat to stay in the building. And it's perhaps worth mentioning at this stage that that applies the other way around as well. So if you're in a very, very hot country and you're going to produce an office building or something like that, then you don't want the heat to get into the building. You want it to stay cool. So in that case, you build the building out of materials, again, that have a low thermal conductivity. A little bit of a story on the side. My mother used to live in a little Welsh cottage, and that had really, really thick stone walls. And stone is a poor conductor of heat. It has a low thermal conductivity. And it was really interesting that without the heating on, the cottage stayed at about the same temperature. So in the winter, it was warm, but it never got really cold. And in the summer, you'd go outside and it would suddenly be really hot, but the cottage inside would still be nice and cool. They must have known something back in the day when they built those buildings. So what I'm going to look at now is what thermal conductivity depends upon. So let's now have a look at what affects how rapidly something loses heat. And this could be something like a thermos flask, a mug, or it could be a building. So maybe it's best to think about buildings. Well, the first thing that heat loss depends upon is the temperature difference between the inside and outside. I guess it's slightly obvious that if it's the same temperature inside the building as it is outside, then it's not going to lose any heat. Whereas if it's much warmer inside than it is outside, it's going to lose heat much more rapidly. It's very warm inside, it's cool outside, and so you've got a large thermal or temperature gradient, so the heat will go out more rapidly. So heat loss of a building, shall we say, depends on the temperature difference between inside and outside. It also depends upon something that we're going to look at in a minute. It depends, of course, on what you build the building out of, the type of material. So I guess it's fairly obvious again, isn't it, that you remember metals conducting heat really, really well. So if you made a building out of metal, and I'm not being particularly silly, they made buildings out of aluminium after the war because there was a lot of aluminium left over from the aircraft industry, then that would have a very high thermal conductivity. Whereas if you build a house out of sort of fluffy material and things like that, like duvet and lagging and brick, etc., then it will stay warm for longer because those materials have a low thermal conductivity. But if you don't put in much insulating material, so for example you have a very thin duvet on your bed, then it won't keep the heat in very well. So it also depends upon the thickness of the material. And I guess that's obvious, okay, that the more insulating material you've got, the less quickly the heat will get out. And finally, one thing that a lot of people forget, the fourth thing that we're going to look at, is the amount of heat loss depends upon the size of the material. Now, what I mean by the size is the area, okay? So it's a difficult one to get your head across here, but if you have a wall in a house that's small, the heat will go through each metre squared of that wall. But if you have a very, very large wall, then each metre squared will lose the same amount of heat, but there's more metres squared. The example I could give you that you're probably familiar with is that if you have small windows in a house, my mother's cottage, it didn't lose heat much. There wasn't much surface area of glass. Whereas if you've got a building that's got large pieces of glass in it, large windows, then it will lose heat more easily through those windows. So we've got to be pretty careful to insulate them. So the fourth thing that heat loss depends upon is the size, or more correctly, the area of the material. And we're going to measure that in metres squared. So now let's have a look at some thermal conductivity values, and so that will allow us to compare the different values, and that's something you might be asked to do at GCSE. So I've gone to the data books and I've picked some typical materials that we could build houses out of. So wood is a good example, and if you look in the data book, wood has a thermal conductivity of 0.1. Now, we're already stuck here because I need to give you the units, and the units are particularly tricky for thermal conductivity, and in the second part of the video I'll look at where those units come from. But what you need to remember is that thermal conductivity tells you how rapidly you're losing heat. So how many joules of heat you're losing per second. You're losing that through a metre squared to make it easy, and then you can multiply that up. And we're thinking of what would happen if our walls, let's say, were a metre thick. It results in a really complicated unit, and you don't need to know the units for GCSE. But I'll put the unit here on anyway. It's measured in watts per metre per degrees C. Now, there's loads of ways to write those units. I've chosen to do it that way. There's another measure of temperature that's a slightly more scientific one, the Kelvin. So it could be in watts per meter per Kelvin, as it were. But you don't need to know that for GCSE. But it's interesting to know that it does depend, the thermal conductivity does take into account how many joules per second of energy you're losing through a surface area. And other videos on YouTube, I think, kind of waffle their way around those units. So, back to the GCSE, let's just compare values. So, wood, 0.1, brick, you can probably guess what brick is like, because we build buildings out of it. It has a thermal conductivity of 0.6, so not dissimilar from wood. Glass, we're a bit more worried about big glass windows, because that has a thermal conductivity of 0.8. Now, I'm going to put one in out of order. Glass wool, this is like fiberglass. It's like, but it isn't, the filling in your duvet. It's that horrible, scratchy, spiky yellow stuff they stick in roofs as lagging that you will have heard mention of in my insulating buildings video. And we'll call that fiberglass or glass wool. So glass wool, the stuff that goes in the roof to insulate, okay? The fact you put that in there must mean it has a very, very low thermal conductivity. So I hope you guess it's a smaller number than these, 0.023, okay? A much lower number, or approximately that. These vary slightly, okay? Now, you remember the video that I did on heat conduction through metals, and some of you have done the experiment in my classroom. Copper. Think about the thermal conductivity for copper. Okay, so it's bonded atoms, like everything else, but it's got free electrons. It conducts heat really, really well, and that has a thermal conductivity of, it surprised me, I'd forgotten this, 385. Many, many times bigger than the other ones here. Now, when we did the experiment, some of you will remember that aluminium conducted not quite as well as copper. So, aluminium comes out at 205. So, have a look at those numbers, and GCSE, think about which ones you would use to build buildings, okay, and compare the values. And the main thing you need to get out of this video is that a small number is a low thermal conductivity, so it doesn't let heat out well. So these guys here, the ones I've done in purple, they're good for buildings. They'll keep the building nice and insulated. And copper and aluminium, now they're going to be no good for buildings at all, okay? They're going to be good for situations where you want heat to travel well, so these are going to be bad for buildings. But good for saucepans. And things like that, for radiators on the wall where we want heat to travel through them. So that's part one of the video, and that covers the GCSE bit. I hope you feel now you've got a good understanding of what is meant by thermal conductivity. The fact there are different values for different materials, and yes, the size of the material matters too when you build things out of it. But most of all, a low number is a low thermal conductivity. It doesn't let heat go through it at all well. So welcome back to the second part of the video, and I said this wasn't going to be particularly easy, so if you're doing GCSE, don't worry too much about this bit. It's moving into A-level territory. But it's good science, and I think you should give it a go just to see how much of it you can understand. So the first thing we're going to look at is the second law of thermodynamics, and you'll hear about laws like this in physics. Okay, so we believe this applies in all situations. Thermodynamics, heat moving. Okay, and what the second law of thermodynamics basically says is that if you've got a hot place next to a cold place, say you've got hot next to cold, it states perhaps something that you think is very obvious, but if that's the case, then the heat energy will always move from the hot place to the cold place on average, and what it will try and do is equalize the temperatures. Okay, so don't think of the cold moving, think of the energy store that's very bunched together, the hot place, letting its energy on average flow into the cold place. The hot place will get colder and the cold place will get warmer until their temperatures level out. So a way of thinking about this is imagine somewhere that is hot, okay, and that's the special place that's been brought in to be next to the place that's kind of the normal place. What I mean by that is that this might be the atmosphere outside, you know, all of the area around the buildings, and this is the special place, a building we've built. And the reason I mention that is that we're going to give the cold place temperature T1, the kind of normal background temperature, and we're going to give the hot place temperature T2. Okay, we're going to put between them a material. So here's our material, and this is the thing that will have the thermal conductivity. We're going to call that K. Okay, it's a constant for that material. Never mind how big you make it, thermal conductivities are fixed values for particular materials. And you'll notice that the heat will try to flow from the hot place to the cold place. And I always draw it like this, high temperature down to low temperature. So you've got the flow of energy, the flow of heat. And what you see here is a thermal gradient. Okay, it's quite interesting that if you think about this in detail, if we made this material in the gap thinner, so push these closer together, that line will be steeper. There'll be a bigger thermal gradient, and the heat will flow more rapidly into the cold place. Okay, I could go on and on about this, but imagine this was a sheet of glass. Okay, one of the things double glazing does is, other than put in a different thermal conductivity overall, is it has the effect of separating the hot region from the cold one and creating less of a sort of gradient here that you see. In fact, the change or difference in temperature will be the same, but I like to think of this line as being a kind of special gradient, one that shows will the heat flow down slowly or more easily. Okay, so the next thing we need to look at is how much material area does the heat flow through. So I'm going to draw over here a section of building or a section of wall. Okay, and I'd like you to think of this side being the hot and this side being the cold. So the heat will try and get out of this material to the cold area. So this side is hot and this is the cold region. So we've got a temperature gradient here, more correctly the difference between T2 and T1. Okay, but there's something else we need to take into account here. How big is this wall? There's a nice way of showing this. It's called heat flux. That if you imagine this heat going through here, if the wall was twice as big, there'd be some heat going through there as well. Okay, so we need to know something about this area here. So this wall has an area. But some of you will notice, but hang on, what happens if we make our duvet, our wall, thicker? So there's another thing we have to take into account. We have to take into the account that this will have some thickness. And if we make this thicker, it will conduct heat not so well. Okay, so for a kind of a fair test, when we make our thermal conductivity values, we need to be looking at the same area, the same temperature difference, and the same thickness. Now, it's going to get a bit confusing. If we use T for thickness, then that gets confused with T for temperature. So this thickness here, we're going to give the little letter L to. That shows us the thickness of the material that we are looking at. So now what I'm going to do is get just a little bit more mathematical. Okay, so here comes the slightly mathematical bit, but it's still good for you to follow if you're doing GCSE, because we're going to look at mathematical relationships. So what does the heat travelling through this material depend upon? Well, we know it depends on the area of the material and its thickness, and it's also going to depend on what the material's made out of. So the thermal conductivity is going to depend upon those things. So we're going to look at the heat flow per second. So the heat flow per second through this material. So if you think about that, the joules flowing per second, the joules per second through this, the watts. Okay, so the watts per metre squared of material. So how much energy flows per second through 1 metre squared of material. Now, what's that going to depend upon? Well, it's going to depend upon the temperature difference. So if there's no temperature difference, the amount of watts, joules per second, going through a metre squared is going to be nothing. Okay, and if there's a big temperature difference, it's going to be a much bigger value. So this is a value that depends upon, that's proportional to the difference in temperature. So T2 minus T1. But remember that the heat flow per second through this metre squared will be less if it's thicker. So it's not going to be proportional to how thick it was, L if you remember, it's going to be inversely proportional, 1 over L. So we've got the two things there that this depends upon. This value, the heat flow per second per metre squared, we're going to give the letter Q to. And Q, as you can see, is going to be measured in heat flow per second. It's going to be measured in watts per metre squared. And I'm going to write it in the A-level way. Okay, watts metres to the minus 2. That's the same as watts per metre squared. So Q is going to be proportional to T2 minus T1 divided by L. Okay, I'll put that lot in brackets. So we've got a value for Q, but we need to make this an equation. We need to put equals in there, and there's something in here, a constant, that will make it equal. Ah, we're finally there. K, the constant. How good this material is at letting heat through it if we have a fixed amount, the thermal conductivity. So I'm going to rewrite this equation as Q equals K T2 minus T1 upon L. And the whole of this video has been working its way towards this little fella, okay, that the value K, yeah, that is the thermal conductivity. And if you remember, that was in watts per metre per degree C, or per Kelvin. I'll do it properly. Per Kelvin. So there we go. The constant in all this heat flow stuff that we've done, this one here, is the thermal conductivity. Good, so I hope you enjoyed that video and you now feel you understand a bit more about thermal conductivity. Remember, for GCSE, it's about the materials you choose. So would you build your house out of brick? Would you build your house out of wood? And what thickness would you use? Or would you build your house out of aluminium left over from old aircraft? And what are the reasons why you would choose those different materials? Also for GCSE, remember that a low number for thermal conductivity means it's kind of a good insulator. It doesn't let heat through it very well. Okay, but taking it further and perhaps a little bit more towards A level, we've now got an understanding of where thermal conductivity comes from. It's the constant in this equation. Anyway, I hope you found that useful and informative. We'll be having another lesson soon, and I look forward to seeing you then.